Hello everyone. In this video we're going to be talking about some quantum mechanical formalism. So before we start actually solving quantum mechanical problems, we're going to need to have a set of tools in hand. So we need to make some definitions and establish some procedures that we're going to use in solving these quantum mechanical problems. Now, there's different ways of approaching this. We could just sort of march into the particle in a box problem and introduce all of these tools as we need them. However, they do sort of form a nice set, and so there's some argument to be made for introducing the formalism first and then going ahead and trying to solve some problems using at least some minimal working set of definitions and procedures. So let's go ahead and do that. And then we can, of course, now the drawback of this approach is that that I'm taking is that we don't really get to necessarily see how these definitions work for a little while until we're finished and with this set of definitions and procedures, and then we can move on to problems. So we may have to circle back and take another look at these concepts as we go, which is fine. So we're going to kind of run through these fairly quickly just to kind of introduce the concepts, and then we'll use them and we'll talk about them in more detail later. So some of these concepts are normalization, which is related to this Born interpretation that we introduced in the last video. So it's related to probability and the Born interpretation. Of the wave function as being a probability density function. Then we'll talk about orthogonality. It's a somewhat mathematically closely related concept, and orthogonality helps us to define states. We see that different wave functions are orthogonal, and therefore they correspond to different states. Then we'll talk about how we implement measurement representations, mathematical representations of measurements of quantum mechanical systems using operators. And operators are part of the tool set. Another part is expectation values. So you calculate expectation values for an operator on a given system represented by a wave function. And expectation values are a statistical property. They're the expected average value of a measurement for a system, for a specific property of a system in a specific state, represented by a wave function. And then there's some interesting properties of wave functions and certain operators, in that some wave functions can be eigenfunctions of operators and they have eigenvalues, and this ends up being very important that we use it again and again in solving a lot of quantum mechanical problems. So we're going to talk about eigenfunctions and eigenvalues. It's a concept that's borrowed from differential equations and linear algebra. So you may have run across this concept before. And then we'll talk about commutation. Again, it's a concept that's borrowed from linear algebra, commutation and commutators. Typical ordinary algebra of functions is commutative, that various functions will commute. The order of operations doesn't matter necessarily if you're multiplying things together. However, in the case of non-commutative algebras, such as linear algebra, that's no longer the case, and we have to define something called a commutator. And finally, we'll talk about something called the superposition principle, which links eigenfunctions, eigenvalues, and expectation values, and gives us our first, or gives us, I don't know if it's our first, but it gives us a glimpse of sort of the dual wave state or multiple wave state that might represent a system. Okay, so I just kind of wanted to get those listed out there so we have a sort of to-do list. Now let's talk about normalization. So we stated previously that the probability of finding a particle in some region between A and B in 1D is psi star of x, psi of x, dx, the integral of that from A to B. Now for that to work, of course, then the integral over all space has to be equal to 0. Or sorry, has to be equal to 1. Okay, so that 1 has to be equal to the integral over all space of psi star psi, where that is a wave function, it's a function of x, and we're integrating it over dx. And I've used this abbreviation a dot s to stand for all space. Now we will run into that again occasionally or fairly frequently in the course of this semester. And that said, we have to be a little bit careful about all space. That allows us to sort of move forward without worrying too much about some details about what the limits of the integral are. But then that means we have to take some care to properly put the limits on the integral when we actually perform the integral. And so that means we often have to go back to the physical picture, the coordinate system, the assumptions that have been made to make sure that the limits on our integral are consistent with all of that. And we'll see some examples of that later. But anyway, so all space, it's not as simple as just saying all space and let it go. It means that there may be some work that we have to do. Now that's for 1D. We say that probability has to be conserved, right? All of the probabilities have to add up to 1. If you're talking about discrete probabilities, if the probabilities of all possible outcomes have to add up to 1. In the case of a continuous probability density, it involves an integral like this. So then that brings up this concept of normalization, in that we may initially have some wave function that is that doesn't quite obey this. It satisfies some other aspects of our quantum mechanical problem. Maybe it's a valid solution to the Schrodinger equation, but when we take the integral over all space, it doesn't integrate to 1. So then in order to be able to apply the Born interpretation and to be able to make probabilistic statements about where our particle is, we're going to have to fix the wave function, and that means we have to normalize the wave function. And so normalization, that's a concept that comes up again, borrowed from math. Things like a normal unit vector has a length of 1, right? And so when we normalize our wave function, we're saying that when we take this integral, it has to add up, it has to integrate to 1. And let me, let's see, and so essentially we'll start with trial solutions of our wave function that are solutions to the Schrodinger equation, and then we'll have to normalize them. And to be a little bit more precise and a little bit more general in that talking about all possible coordinate systems, we define something called normalization. We say that psi is normalized if the integral over all space psi star psi d tau equals 1, where d tau is a generalized volume element. Okay, and that's supposed to be a tau there, right? D tau. A Greek symbol. Looks a little bit like a T. Okay, so then if this is true, and again, defining all space as we did above, then we say that, then we can say that psi is normalized. Okay, and then let me circle back to d tau. What do I mean by d tau? Again, this is just kind of a way of talking about a general case. We may have quantum mechanical problems that are essentially one-dimensional in nature. There's really no sense in introducing other dimensions. They're just sort of spectator dimensions. So d tau, what it is, depends on the nature of the problem. If we're talking about 1D, then it's something like dx. If it's 3D in Cartesian coordinates, then it would be dx, dy, dz. And if it's in spherical polar coordinates, it's a little bit more complicated. There's this expression r squared dr sine theta d theta d phi, and that's your volume element in spherical polar coordinates. 3D spherical polar coordinates. And so this integral over all space will often be, say, a triple integral over all of the different dimensions. You have to integrate all of the various dimensions so that we get a scalar number as the result. And then we compare that to 1. So in the case of, say, a Cartesian integral over all space, then our integral is going to look like it's going to be a triple integral. X equals minus infinity to infinity, y equals minus infinity to infinity, z equals minus infinity to infinity of psi star psi, and these psi's would be functions of x, y, and z, and then of course we have the differential volume element Okay, and that's assuming that our wave function in fact spans over all this space. Sometimes we define all space differently, as you'll see when we get into the particle in a box. And for spherical polar coordinates, we're not going to use them for a little while, but just to kind of remind you that they're there and they will appear, the integral would be not from r equals minus infinity to infinity, it would be r equals 0. That's usually the limits set for r 0 to infinity, in the way that spherical polar coordinates are typically defined. Those are the limits. And we have to be sure to set these limits in such a way that we don't double count. So if we set it to minus infinity to infinity and we didn't change the limits on our angles to sort of match, then we're going to end up integrating over our function multiple times, and that would be an invalid integral. So we have to be very careful about our limits. That said, we'll circle back to this later. And by the way, these are integral symbols. They're not just kind of big lazy S's. So theta would go from 0 to 2 pi. And phi, there are different kinds of spherical polar coordinates, but one way to define it is that theta goes from 0 to 2 pi. And we'll see that later. And then phi would go from 0 to pi. And that would be psi star psi, where that psi would be a function of r, theta, and phi. And then our differential volume element, we would have to multiply by r squared, dr, sine theta, d theta, d phi. Okay, none of this should be new as far as these coordinates. However, it's not necessarily something that you run into every day. But we're bringing it, showing it to sort of remind you of this concept. Okay, then we will want to normalize the wave functions, but I'll talk about how to do that in a little bit. Next, we'll bring up the concept of orthogonality. And orthogonality has a similar expression. So far I've said a wave function is not necessarily the wave function. There are different wave functions. There may be different states of a system. In fact, if all our systems were in one state, then there wouldn't be really much for us to do. And so there are different states, and we sort of know that already, right? We know that, say, hydrogen atom has 1s states and 2s states and so on. And so we may be somewhat familiar with this concept of there being different states in a system. And that brings us to orthogonality. We say that if we have two wave functions, psi I, psi j, they may look similar, they may not. We say that they are orthogonal if the integral over all space of psi I star psi j d tau equals 0. So again, we're borrowing a concept from mathematics, from trigonometry, and it's sort of similar to the borrowing the concept of normality, but this is a slightly different concept of orthogonality than what you see in trig. Here we're talking about functions, and functions being orthogonal to each other. These functions are necessarily associated with any sort of angle. they're not at right angles to each other in a trigonometric sense. They're at right angles to each other in a sort of function space sense, sometimes what's called a Hilbert space sense, but that's just some fancy terminology that we won't get a chance to talk about much of this semester. But if we multiply these two functions together, integrate over all space, supply the correct differential volume element, and it integrates out to 0, then we say that the wave functions are orthogonal. And also, this has an important implication. This allows us to define whether or not two wave functions correspond to different states. So they're orthogonal and they correspond to different states. To two different states. And so now we have a tool in our toolbox. If we have two wave functions and they may look somewhat similar and we're wondering whether or not they in fact do correspond to different states, we can perform this test and determine whether or not that's true. If the integral ends up being non-zero, whether it's ends up giving you some real constant or complex constant, then they're not orthogonal. So they have some overlap, we say. In other words, it's sort of like two angles that are not quite at right angles to each other, or maybe they're actually parallel angles. And so even though the functional form may look rather different, by this test, this is kind of an equalizer. It sort of allows us to test and cut through any sort of confusion or ambiguity about the algebraic form and determine once and for all whether or not these correspond to different states. Now, another way that this ends up being useful is that we can use this orthogonality relationship to sometimes, once we have one state, we can make a guess about, say, what another state is going to look like. And maybe that guess function is going to have some parameters in it. And so then we can set up this orthogonality integral and determine what those parameters are that will give rise to another state that's different from the state that we started with. And so this kind of leads us towards this this kind of induction approach where we solve a special case and then we find additional cases, and then we can get the full sort of spectrum of what the states are in the system. We can get the list of all the states. So this is useful in a couple of ways. One, it's a good test. Another thing is sometimes it can be used to generate additional states. And when we have a set of states that are orthogonal, we also would want them to be normalized. It turns out that there's a lot of use for having a set of wave functions that are to have two or more or a whole collection of states that are orthogonal to each other, and each state itself is, each wave function, which corresponds to a state, is normalized. And let me circle back on something there. So I may have neglected or very quickly stated that wave functions represent states of a system. And at least it's been sort of implicit in what we've been talking about. And so we're getting into some of the details about whether states are different. And so we say that two wave functions are orthonormal if psi I, and psi j are orthonormal if they are orthogonal to each other and each state itself is normalized. So each one of these wave functions would be normalized. So one would be equal to integral of psi I star psi I d tau over all space, and the same would hold true for wave function j. And so that would be for two of these wave functions, and we can imagine there being an orthonormal set of wave functions, I, j, k, and so on, or 1, 2, 3, 4, 5, whatever your index is, or ABC. There can be an orthonormal set, and those are useful. Those end up forming something called a basis set. And basis sets end up being used. It may be a term that you could have run across if you've had a chance to work a little bit with some quantum chemical software. One of the things that you can choose is what is the basis set that's used for the calculation. And so basis sets are an important concept and something that we'll come back to later when we're talking about much more complicated quantum mechanical problems, such as those involved in things like chemical bonding. Okay, then one final thing, let's introduce something called a Kronecker delta. And this is delta ij. It's a way of sort of combining the orthogonality and the normality together in one expression. And we say that psi I, psi j are orthonormal if this integral over all space psi I star psi j d tau equals delta ij, where delta ij, those could be two different or the same integer. So it would be equal to 1 if I equals j, so where I is 1 and j is 1, or I is 2 and j is 2, and equal to 0 if I and j are different labels or different integers for these wave functions. Okay, now let's talk a little bit about, so now we have a few concepts under our belt, and now let's move on to states and wave functions. Yeah, here's where I was going to bring it in. So I've so far implicitly said states and wave functions are kind of the same thing in that the state is the sort of state of the real system, and the wave function is its representation. mathematically. Okay, and the wave function, in fact, completely defines the state of the system. And orthogonal wave functions correspond to different states with different properties. And typically they'll have at least one different property, although they may have some properties in common. You may have two electrons that have the same spin and thus have the same spin quantum number, and the spin part of the wave function is the same, but they might have something else different about them. They might have different energy. Okay, so there are a lot of different properties, which of course we haven't had a chance to go into in any detail yet. And that, I think, is a good stopping point for this lecture. Next lecture, we'll talk about operators and observables.